What's up to you all awesome and wonderful matriculants? Welcome to our Physical Sciences Tuesday. I hope you missed this because we did miss you guys. On the page, there are some mindsetters that said they couldn't wait for the show. So guys, welcome. My name is Abram and today's show we're having it with the one and only Tracy. Where have you been, Tracy?
Sorry, I had duties at school. I couldn't get off. I had to look after the detention children.
Welcome back.
Thank you. I'd much rather be here.
Welcome back.
Yeah.
You know, having a John show last week.
It's always fun. I saw part of it. I was like, no, it's cool. John gets just as excited.
All right, let's keep last week to last week.
Yeah,
All right,
okay.
get into details. What are we doing today?
Well, today we're getting back into chemistry. And guys, we're going to look at rates of reaction, which you may or may not have got to. I'm not sure. Depends on how you're doing. But it's actually a really nice section. It's another one of those sections where you did a little bit of it last year. Now we're just going to add to it. And there are some calculations and graphs, but actually it's quite nice. It's a nice section.
Sounds fun. I can't wait for it. And already there's some mindsetters that are watching, such as Nkosinathi Naga. And a big shout out to you. I was watching the show, and every other person that is watching right now, let us know on facebook.com/LearnExtra, or simply send us a tweet at LearnExtra. We're here to help you guys. If you're struggling, don't hesitate. I'm your guy. Let me know. Remember, the notes that Trace is going over are from this awesome workbook, of which you can get for yourself for only 139 Rand. Simply send an email to sales@mindset.co.za and we'll hook you up. This show is proudly brought to you by the Department of Basic Education. Tracy, over to you.
Guys, get the workbook. I think it's brilliant, and I'm not biased at all, but it's got lots of exercises. Okay, so we start in rates. And so what we're going to look at, we're going to look at energy change. That's revision from grade 11. We're going to look at heat of reaction or enthalpy, also a little bit of grade 11, collision theory, factors that influence rates, and then how to measure rate, the things that we would do, okay? But now, we have a challenge question for you. Okay, so a little bit different, but I promise it has to do with rates. It really does eventually. Okay, so this is my challenge. And it's up to date because I only found out about this morning, and I'm horrified. It's okay, I'll get over it. How do you think climate change or global warming, we lump them in together, is going to affect you directly, especially in the morning? So how do you think global warming is going to affect you directly? Do you know? Do we have some answers?
I do know. I'll tell you later.
You tell me. Okay. So just have a think about it. It's a little different to what you expect. I think we know the normal, it's going to be hot or cold. Just going to put it out there, okay? We'll see how many of you get there. If any of my own learners are watching, you will know you must be grateful you're leaving school soon.
And I must say, I've already posted the challenge question on our Facebook page.
Have we got answers yet?
We do have some answers.
Oh, this is going to be exciting. I'm looking forward to actually doing this one. All right, so let's actually do the theory, shall we? So, if we look at rates of reaction, okay, the first thing is we need to talk about the energy change that takes place. And remember that we need to have activation energy. So a reaction can't begin until we have activation energy. That is the absolute minimum amount of energy needed for the reaction to take place. That is whether the reaction is spontaneous or not, it doesn't matter, okay? Now, this energy, this whole concept here, and this, I'll try not to close the note, shall I? All right, this whole concept here of an energy hill, that some of your teachers may have used that concept, may not have, but when you did graphs, it almost looks like the reactants have to gain energy and they have to climb up a little hill first and then they go down the other side, okay? So that energy hill is the amount of energy we need to put in, which is our activation energy. When we've put in the activation energy, we get to a middle step, which is known as the activated complex, okay? So what we have here is we have substance AB, whatever it is, added to C, and we get this little thing in the middle, ABC. Guys, this activated complex is not stable. I can't take it out of the system and use it for something, okay? When we get to that activated complex, then now a decision has to be made. Either those atoms are going to break apart and go back to what they started as, the reactants, or they're going to now form new bonds and form the products, okay? So this activated complex is like a halfway stage. It's neither a product nor a reactant, but you can't take it out. You can't do anything with it. It is temporary and it is incredibly unstable. Okay, so you can't do anything with that. Once we get that activated complex, it now makes a decision. I'm going to make products or I'm going to make reactants. It'll make reactants if it doesn't have enough energy. So if we haven't put enough activation energy in, it's going to go back to the reactants. Okay? And that is whether the reaction is reversible or not is irrelevant. That's what's going to happen there. Okay? So, now, heat of reaction. This you've seen, also known as enthalpy. Funny name, doesn't matter. Delta H, heat of reaction. You will also be called change of enthalpy sometimes, so get used to the word enthalpy. Heat of reaction makes more sense in my head anyway because it's delta H. And your heat of reaction is the difference between the energy of the products and the energy of the reactants. And it absolutely can be negative. Don't go, it's got to be big minus small. Remember, this is a change in value. And whenever we do the change in something, it's always final minus initial. So that means it's got to be products minus reactants for energy. Okay? So from grade 11, for an endothermic reaction, you remember this? My products have more energy than my reactants. So we have a positive delta H, and it will appear while the system gets colder. So if you have to touch the reaction, it'll actually get cold. Okay? Good example of this that you see all the time is those disposable ice packs. When you break them, okay, they create an endothermic reaction which makes it go cold. Okay? Not like those click heat pads. You've seen them?
Yeah.
That's an exothermic reaction, which you can reverse, okay? For an exothermic reaction, it's the other way around. Our products have more energy than our reactants, which is also why we get a negative value, because this is a smaller value, products is a smaller value minus a big value, okay? And the difference, my delta H, is positive, is negative, and that we feel is heat. Most chemical reactions are actually exothermic. At school level, we don't deal with a lot that are endothermic, but it's not beyond the scope of what we do. Now, remember, we can add a catalyst. A catalyst is a very important part of our chemistry. A catalyst is defined as a substance which can change the rate of reaction. At school level, we actually only use positive catalysts. So that means we're actually using a catalyst that can increase the rate or make the reaction go faster, okay? Speeds up the reaction. A catalyst doesn't take part in the reaction and doesn't undergo permanent change. That means that it can change phase or maybe change from being a solid to a powder or something like that, though that's quite rare, but it doesn't undergo anything that's permanent, and it doesn't undergo any chemical change at all. So, when we put a catalyst in, what is its function? It provides an alternative route for the reaction to take place. How does it do that? It lowers the activation energy, okay? So, when we go to our reaction, this dotted line over here, which I know I'm now going to put in yellow, that's what the activation energy does. So originally for this reaction, I needed all of this energy here, this long, funny orangey colored line. That's how much energy I needed to give to the reactants to get to the activator complex to then get to the products. I add in a catalyst, and the catalyst now says, well, no, hello, let's only use that much energy. I can halve it, I can quarter it, doesn't actually matter, but I change the activation energy. What's really important here to note, delta H doesn't change, okay? Delta H stays the same. You cannot change the enthalpy. Whatever it is, that's a constant for that reaction. We can change the activation energy, but nothing else, okay? Because that delta H is determined by the bond energy of the reactants and the bond energy of the products. If you remember in grade 11, you had to do those calculations where you actually had to work out bond energy, and you had to first work out how much energy it takes to break the original bonds, and then how much energy will be given when the new bonds are made, and then you had to minus them. That's a constant. Whether there's a I'll try that again. Whether there's a catalyst or not. I think we'll talk slowly. This is because I have not had enough coffee today. We had no power at my school from 11 o'clock this morning. I'll move on. All right, so collision theory. Guys, they are going to ask you about collision theory. Okay, it's one of those things that they're going to do now. Collision theory says to us that in order for a chemical reaction to take place, the atoms or the substances have to, now wait for it, collide. It's called collision theory, okay? How they collide is very important. So they have to collide. Not all the collisions mean that there's going to be reaction. They have to collide with an effective collision, okay? And to get an effective collision, they need to collide with the correct orientation. I can't even spell. Correct. See, that's a C. Orientation. Okay, so they have to hit each other in the same way, and they have to have sufficient energy. All right? Sufficient kinetic energy. Correct orientation, not much we can do about it. They have to actually hit each other in exactly the right way, otherwise they'll just bounce off each other. And sufficient energy, remember that when they hit each other, there's got to be enough energy for the old bonds to break and the new bonds to be made. Okay, so there's got to be enough energy in there. If we can't get this right, then it won't be an effective collision. So here, the whole point is to increase the rate of a reaction, we have to increase the number of effective collisions. We can do nothing about correct orientation. So we can't take out a pair of atomic microscopic tweezers and like manipulate them like building blocks, as much as that fun that would be. Okay, but we can increase the amount of energy we have, and we can increase the probability of how they collide with each other, okay? And how do we do that? Well, five things, I apologize. First is temperature. These are easy ones to remember. Increase the temperature, we always increase the rate. Why? Because if I increase the temperature of my system, I increase the energy of my particles, therefore more particles will have sufficient energy. If they have sufficient energy, then the collisions are effective. That's pretty straightforward. Pressure, only with gases, okay? Only with gases. Please, 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 they're going to try and trick you out here. Solids and liquids, pressure doesn't affect them, okay? You can't increase the pressure on a solid, you can't increase the pressure on a liquid. You can on a gas, but only if it's a closed container. If it's open to the environment, then pressure does nothing as well. Remember, pressure from your gas laws from last year, if I increase the pressure generally, that means I'm going to make the volume smaller. If I make the volume smaller, I'm actually increasing concentration. But if I make the volume smaller, then there's a smaller space, and if there's a smaller space, then more of them are going to collide. More collisions we have, the more likely it is to be effective, okay? The next one is concentration. Okay, this only affects aqueous solutions, okay? No solids, no liquids, and it affects gases, okay? Concentration, the more concentrated something is, the more particles there are. If there's more particles, then we'll have more collisions. If there's more collisions, they're more likely to be effective. Okay, I think we're getting this. State of division, some of you might get this as surface area. That's when we go from big chunks to tiny little powder pieces. Powder has a greater state of division. The more divided up it is, the more likely it is to go fast because we have more particles available, okay? A catalyst decreases activation energy, more particles have sufficient energy. And then nature of reacting substances. That's the only one I can do nothing about. Some things just react quickly. Some things just don't. If we look at our metals, if we look at sodium and gold, we put them in water, the gold will sit there for centuries and nothing will happen to it, okay? The sodium, you put it into water and straight away it reacts. That's just the way it is. There's nothing we can do about that, okay? And then last thing before we take a break, the things we can do to measure rate, practically. Number one, we can measure how the reactants disappear. So we can actually time how long it takes for us for the reactants to dissolve, or for products to form. So if it forms a product that's not soluble, then we can see how long it takes for that solid to form. We can look at color change. Now, we can do that by comparing it to color cards or using a spectrophotometer, I probably said that wrong, We don't have these at school level, just so you know. That's just a special little meter that measures the intensity of light and the color. Okay, so it measures the frequency. That's just for like really fancy stuff. We can look at conductivity, concentration of ions. The more concentrated they are, the better they are at conducting electricity. We can look at gas volume. They love gas volume produced. We can look at mass changes, whether the mass of the product's increasing, the mass of the reactants changing, and of course, the volume of a solid form. That's a little bit more difficult. The ones you're going to see more often, gas volume produced and mass changes. Sure, that's a lot of talking. So I think it's time for a break, and then we'll jump into the questions.
Awesome, guys. During this break, we've got an exciting competition just for you matriculants because we love taking care of you. So take a look at this, and we'll tell you more about it after the break. Welcome back with some matriculants. Now, you've just seen that promo. It's so awesome, guys. We're giving you courtesy of South Point 1 year of free accommodation, and entering is simple. All you need to do is to fill in the form that I've already posted the link for you on facebook.com/learnextra. That link will take you to our website, and you fill in that form. And it's easy. Your name is on the draw, and you could win yourself that accommodation next year. Because I know, varsity, you agree with me, Tracy. Getting accommodation is a nightmare.
And it's expensive.
It's very
I
expensive.
would have killed for that opportunity.
So you need to worry about books, you need to worry about other things, and accommodation.
And that often limits where you can go because you can't afford the accommodation.
Of course,
So
of course.
And then if you get nice accommodation, these things you have to pay for transport. And with the petrol price, hello, you can afford transport.
So
you know.
here's an opportunity.
I think
free
it's brilliant.
accommodation. It's brilliant. Guys,
I think it's
I must
brilliant.
encourage you as well to send through your questions on what we're going over. I've seen some of your comments. You're enjoying the show. It's awesome. But let's keep your questions coming and help one another on the page because we're into this together.
Absolutely. Okay, so let's jump into this
Yes.
one. This is from the Gauteng Prelim 2012. Okay, and it says to us, and we've chosen these questions deliberately because it gives us a nice range of questions, but also this section lends itself to skills questions like what is an investigative question and safety measures and all of those sort of things, okay? So a student uses the apparatus below to investigate the rate of reaction between iron and sulfuric acid. The balanced equation for the reaction is, we like it when they give us a balanced equation. Now, first of all, there's a couple of things we need to notice here. One, it's not reversible, okay? I know that because they didn't give me a reversible sign. And two, with the setup, okay, it's not actually a closed system. So reversible reactions, which you're going to start next week, it must be closed, okay? So what we have the iron powder, the sulfuric acid goes in. We know we're getting hydrogen gas, so it's obviously the hydrogen gas that's been bubbled through the water into the measuring cylinder, okay? So the first thing is, describe how this apparatus can be used to investigate the rate, now listen carefully, of this reaction. Guys, be careful. Now, we just went through different ways of measuring rate. Color, volume, of the solid, mass, all sorts of things. They don't want that. They want of this reaction. Now, in this reaction, we're producing hydrogen gas. That means I can use the measuring cylinder to measure the volume of hydrogen gas produced. Okay, so for this reaction, I'm going to, and it's worth 3 marks, okay? So we go, well, H2 gas is produced, okay? So because we're producing a gas, we would measure, and I'm going to run out of space, and that's just not even vaguely legible. We measure volume of gas. But remember, we want a rate. Rate implies time. So just measuring the volume, I can't just go 20 centimeters cubed, 30, 40, whatever. Volume of gas per unit time. Now here, that unit time, grade 12s, could be hours, could be days, could be minutes, could be seconds. Probably in this situation, you would do it in seconds. You'd probably measure the volume every 10 seconds. 30 seconds, you wouldn't measure it in hours, because in the first hour it'd be finished. Definitely wouldn't measure it in days, okay? But the unit time has to be valid for the experiment. So some things you measure in seconds, time can be in minutes, hours. It depends on the reaction. Also, what your volume would be measured in depends on your measuring cylinder. So you could measure it in milliliters, you could measure it in centimeters cubed, could be decimeters cubed. There's no real SI unit. It depends on your apparatus. Okay? Now, define the term reaction rate in terms of, look here, this reaction. Now, you have just told me, or I've told you, that we will measure the volume of the gas per unit time, which means the rate of this reaction is the rate at which hydrogen gas is produced. Okay? So the reaction rate for this equation, for this reaction, is the volume of hydrogen gas produced per unit time. Reaction rate is how fast or slow the reaction goes. General. Now we need to put it in specific, which is the hydrogen. Okay? Now, the student repeats the experiment with different concentrations of sulfuric acid. So what we're doing here is they are investigating the factor of concentration. So they're saying what happens with concentration to the rate. And all other variables are kept the same, and here they give me the results. So concentration of my sulfuric acid, they measured it in centimeters cubed per second. Okay? And we look and we go, well, at 0.4, it was 4.2 centimeters per second. 0.8 jumps to 8.5 centimeters cubed per second. At 1.6, it jumps to 17 centimeters per second. Centimeters cubed per second. Guys, this is not a direct proportion, by the way. Okay? Not quite. Not quite directly proportional. Now they say to us, 3 variables that must be controlled. Guys, these will be variables that affect the rate. Okay? So I'm not talking about we must keep the glassware clean, or we must use the same measurements. That's not what we're talking about. We're changing temperature. The other things that can be concentration, sorry. The other things that affect rate. So here we need to keep starting temperature constant. Why can I not just say temperature? Because I know that's what some of you would say. Because the end temperature is not going to be the same. This is an exothermic reaction, all right? Because it's an acid with a metal. It's an exothermic reaction. In an exothermic reaction, we're going to get certain amounts of heat given off. The heat given off, the amount of heat given off is going to be determined by how much stuff we start with. But how fast it gets there is determined by starting temperature. So I must keep starting temperature the same. I changed concentration. The third thing I need to keep the same is the state of division of the ion. Okay? Now, don't just say state of division, because do you mean the sulfuric acid? Do you mean the ion? Do you mean the hydrogen? Okay? So you need to state of the ion. Remember, if the ion is in solid big chunks, it'll go slowly. If it's in powder form, it'll go much faster. So we need to keep that constant. But with another thing with the ion that we need to keep constant is the mass. Now, that's not got anything to do with concentration, but remember, if we change the mass of the ion, we're going to change how much hydrogen we form at the end. And if we draw a graph, it will be different. Okay, so we don't want to change the mass of the ion. We need to keep the mass of the ion constant. Okay, now, write down an investigative question. We love this, for this investigation. So now we've just discovered, we know what we need to keep constant. The temperature, the concentration, not the concentration, the temperature, the mass, and the state of division of the ion. We're looking at how concentration of the sulfuric acid affects the rate of reaction. Now, with an investigative question, you cannot start with these words, does or will. An investigative question must be a question that can be answered with a sentence. Cannot be a question that can be answered with just a straight yes or no. So you can't say, does the concentration of the acid affect the rate of reaction? Because you can answer that with a yes or a no. Or will the concentration of the acid affect the rate of the reaction? Well, you can answer that with a yes or a no. It's got to be a statement. That statement must include dependent variable, independent variable, and your constant. Independent is the thing we're changing, that's concentration. Dependent is the thing we are measuring, which is not actually the volume of the gas, it's the rate of the reaction, okay? And constants, temperature, etc. So, when we write this one down, okay, is good way to do this is to say, what? This is a good way to start one of these. What is the relationship? They love the word relationship, okay? Okay. Between, and now we're going to do our variables between the, let's put it there, the concentration. Now here, if you said sulfuric acid or one of the or a reactant, either way, it doesn't matter, of, let's put, of sulfuric acid, and the rate of reaction, provided, now watch, here's our variables, our constants, provided all other variables are constant. And I ran out of space. Let's pretend I will leave myself enough constant. There we go. Now, very important, what do we end a question with? A question mark. It's a lot of writing for 2 marks, but they want to know, do you know the dependent, independent variables, and do you know what the constant is? And do you know there has to be a relationship between them? Okay? Because remember, a lot of the stuff we do, we want to get to relationships where we have indirect proportion, direct proportion, or even been able to say if one increases, the other increases, one decreases, the other decreases, or increase and decrease, whatever the case may be. Now, write down a conclusion that can be drawn from this result. What did we see when we look here? As the concentration increased, the rate increased. Please be careful here, because I see this often, is you go, as the concentration increased, the time increased. No, the time actually got smaller. The time for the reaction gets slower, so the rate increases. If it takes less time for the reaction to take place, the reaction rate is faster. Okay, so what conclusion can we form? Well, an increase in, and another way to write concentration is like this: increase the concentration of the H2SO4 will lead to, okay, or gives an increase in rate, or in reaction rate. Okay, so if we increase the concentration, the rate of reaction will increase. Simple as that. Now, how will the reaction rate change if lumps of iron are used instead of iron powder? Well, if lumps are used instead of powder, we're making the stated divisions bigger. Okay, bigger pieces, smaller rate. That means my answer here is decrease. Oh, look at that. That was nice and easy. How will the reaction rate of reaction change if it is carried out at 20 degrees rather than 30 degrees? Lower temperature, smaller rate. That means it will also, oh, good, decrease. Thought I'd give you a calligraphy lesson in the middle as well. You guys all okay with that? It's not a bad section we get in there, all right? So, do you think we have time to quickly jump in one more question?
Yes.
Yeah? Okay. And this one's quick, you'll see. This type of question probably falls into our level 1, level 2 category, guys, where it gets put in and you want one of these questions because it really is nice. So, also from the 2012 paper from Krating, the graph below represents the energy changes according to the reaction carbon monoxide plus nitrogen dioxide gives me carbon dioxide and nitrogen monoxide. Before I even look at the graph, okay, first of all, potential energy minus 40, minus 170, minus 400. That's okay. It's a little unusual in terms of a scale, but that's not a train smash. These are my reactants. My reactants start at minus 170, and I'm going to take that off so you can see it. And the nice thing about this graph, and they will always do this, is if you look carefully, is this will corresponds exactly with, not my very skew line, with the reaction, the energy of the products, okay? Your graphs will always, if they're not completely accurately drawn, they'll show you exactly where your results need to be read from, okay? So they're not going to give you something like this and then make you take your ruler and try and work out what the scale is, because these are ridiculous numbers, okay, to try and work out a scale. They're never going to do that. So now the first thing they'll ask you is calculate delta H for the forward reaction. Forward reaction means I'm going from here, I'm going up the hill, and I'm coming to here. So my delta H is, remember, delta H is the difference between the energy of my products and the energy of my reactants. So now we look at the graph and we go, well, the products have an energy of minus 400 and my reactants have an energy of minus 70. So this means I've got minus 400 minus 170. Okay, that's going to give me minus 230 kilojoules. Now, before I get the units, I look at the graph, and the units on the graph are kilojoules per mole. So my answer is kilojoules per mole. I'm just going to double check because you never know how bad the maths can be on a live show. You guys, not so bad. Now it says calculate the activation energy, very important here, for the reverse reaction. So now for the reverse reaction, we're going the other way around. And your activation energy is the difference from here to here. Okay? That's my activation energy. So I'm going to take my final energy is minus 40. My initial is 400. There isn't actually an equation here. So my activation energy is the final energy it needs to get to, which is minus 40, minus the original energy, which means it's 360 kilojoules per mole. That's fairly high, okay? Now, look at this. Use collision theory and explain why the rate of reaction increases with an increase in temperature. Well, increase in temperature increases the kinetic energy of the particles. More particles have sufficient energy. Therefore, more of the collisions will be effective, and then the rate of reaction increases. Increase in kinetic energy, more particles with sufficient energy, more effective collisions increases the rate. Nice and simple, okay? And, look, what would the effect of a catalyst be on the activation energy? We spoke about that. What does catalyst do? Lowers the activation energy. Lowers the activation energy. What does it do to delta H? The answer? Nothing. Absolutely nothing. Now I want you to see something quickly before we take a break. Delta H for my forward reaction, we worked it out to be minus 230, okay? So delta H, that was horrific. Delta H for my forward reaction is minus 230 kilojoules per mole. Delta H for the reverse reaction, for going this way around, okay, for the reverse reaction, is positive 230 kilojoules per mole. It's exactly the same, just one's negative, one's positive. Because the difference in this energy, whether you're going forward or backwards, is exactly the same. The reactants or products will have the same energy beginning and end. Okay, I think it's time for a break.
Yes, of course. And I've got some great comments here from the Mindsetters. Charlene saying, Lane Extra is doing so well. I'm tuned in. Thank you, Charlene. And other Mindset, most of these guys are watching with their friends and brothers.
With their brothers. Last time it was moms.
Kulufelo says, enjoying the show with my brother.
Brilliant. Love it.
Well,
last time it was moms, remember?
Yeah. And
love
it should still be moms even this week because we are towards Mother's Day.
Yes.
So if
But maybe mom shouldn't have to hold their hand this time. They should reward mom for being
where
so
are the
good.
dads? Okay.
Let's not go
That's
there.
another story for another day.
Yes.
Guys, talking about giveaways, still in the spirit of giving, take a look at this and I'll tell you more about this awesome competition, the Beer Bright Spark competition. You don't want to miss it. Welcome back to the most exciting segment of the show, guys. You've just seen the promo about the Beer Bright Spark. So entering is simple. You just buy yourself the Safeways K53 manual or download the Cool Android app, which is available from Samsung Galaxy App Store or from Google Play for only 59 rands, guys. Then you jump into our Facebook page, facebook.com/LearnExtra, like it, and go to Safeways page, like it, and also fill in the entry form because we want to get your details. And you could be driving off with that new Chevy Spark L, just like Dimaka. So I wish I could win, but unfortunately it's for you. So enter right now. Tracy?
No, it's all these competitions, yes.
Yeah, we're not
Enter.
allowed to enter any
no.
competition. It's fine.
Anyway,
Let's get to the challenge
let's
question.
get to the challenge
I'll get some
question.
answers.
So, I asked you, how do you think climate change is going to affect you, especially in the mornings? And we've gone through some of the answers. Some of them are quite interesting. I can see that you get hammered climate change at school. You can tell. And some of you do geography. You so can tell. So we're going to talk through some of them, and then I'll tell you what I was looking for. Okay. Let's go.
What happened now?
Look, it's all gone. Okay, yes.
Okay, the first one is from, let me take a tweet for you.
Okay.
The first one, it's a tweet that came first from, told you now, wait a second.
Technology.
When technology fails.
Yes. Oh dear.
It's from @DM Ntembi.
Okay.
Ntembi says, in my opinion, it's because at night CO2 is not absorbed. It leads to more global warming.
Okay, I'm assuming you mean by the plants, maybe. I don't do biology, so I'm not sure if that would affect, maybe because it's too hot. I don't actually know. So maybe. I don't know.
Okay.
Yeah?
Here's the one that you like.
Yes.
Tindani May says, people like me with allergies could suffer more as rising temperatures in the morning cause more abundant allergen blooms and longer allergy seasons.
Sure, I like that one. I think that's also good. That's quite relatable to rates as well. And I am talking a little bit off the top of my head because obviously with the rise in temperature, your seeds are going to burst more often, okay, because your fruit and all of those sort of things are going to ripen faster in some cases, and perhaps they'll be drier as well. I mean, with allergens, that's a real problem. I would hate to I have as well, but longer allergen seasons doesn't appeal to me at all. But I think that's a possibility, definitely. Have we got anything else?
Yes.
You want to do a couple more before I do the answer?
Okay, Kulufelo Sydney Munyausi says, due to the rapid increase of the temperature, it will cause our normal body metabolic processes not to function properly. It can also lead to skin cancer due to high ultraviolet rays. In the morning, it will also affect our body functions as we are used to a certain temperature that might change due to global warming.
That might. I think we might adapt quite quickly as humans. I think we will adapt to the rising temperatures more than we'll eventually not even notice. But because you knew what the answer had to be for today, correct? Did anyone get there?
No.
Okay. This is one of, and this is quite sad. The actual answer, and are you prepared for this? Okay, because this shocked the socks off me. And I found this out this morning. My matrics are dying right now. You won't be able to wake up to a cup of coffee in the morning. Because global warming is affecting how coffee is being produced. In fact, a professor from a PhD student from WITS has just released, so our own WITS University, very proudly South African, has just done a study, and I'll give you the website you can go to, where they looked at the coffee industry in Tanzania particularly, where they grow coffee beans at 1,000 to 2,300 meters up, where the temperatures are cooler. All right, so the cooler temperatures are really good for the coffee bean. And in fact, the one we're using, they use coffee Arabica, which would be Coffea Arabica, which is Arabica coffee, which we all know, okay? And in fact, ideal growing temperatures are around 15 degrees at night. And in fact, Coffee yields in Tanzania have diminished significantly from 1961 to 2012 when they were busy doing the studies. So it's not just, look, obviously from a more serious point of view, people are losing their jobs, the small farmer can't keep up, and now they're growing other crops. But for those of us who are serious coffeeholics and need their caffeine, this is a real problem, okay? Because watch here. Coffee Arabica is actually a very special flowering plant, okay? And its seeds become coffee beans. But the berries, those beans, are incredibly sensitive. So they need to have a relatively low temperature. Now, Tanzania is quite high up, so it's got a very moderate climate anyway. I mean, their nights will be warmer than ours anyway, okay? But what they found, okay, is at night, if the temperature is 15 degrees or higher, this is why I like the whole thing about our answer with the metabolism, the plant's metabolism changes. So now what happens is it doesn't produce coffee anymore because its metabolism has changed, so our yield is lower, and it's a bad quality. You can't actually consume it. So that's a problem. And in fact, for every 1 degree rise in minimum temperature, the annual loss is approximately 137 kilograms per hectare, which is 10,000 meters squared. Doesn't sound like much, but that's a lot of coffee in terms of a farmer. In fact, the smaller farmers in Tanzania only produce just over 200 kilograms per hectare anyway. So that's a lot to be losing in production, okay? And if you do want more, it's at www.scienceofcoffee.org. But what I want you to see here is I've just told you that if we increase the temperature of a reaction, we increase the rate, okay? So here, the higher temperature isn't making the rate increase. So you would think, well, if the rate increases, then we should get more. Just because the rate increases doesn't mean we get a better yield, okay? And here we're looking about a yield in terms of usable product. So when we get this increase in temperature, our product isn't usable. So yes, we get in it, it's possibly getting a bit faster, but it's not good coffee. So this is very sad for someone like me. I think it's an interesting study. They also reckon it's going to affect countries like Brazil, the South American countries that produce such nice coffee. So as silly as it sounds, okay, global warming, this is one of the first studies that have actually been done, and I'm proudly South African to say it was done by a South African, where we can actually see, where they can see a genuine effect on a crop. Because sometimes it all feels like it's all up in the air and people think, yeah, it is and it isn't. But they've noticed it over a number of years. But 1 degree in temperature, 1 degree. It's not about time, okay? It's 1 degree. And that would be your average temperature, okay, over a period of time. So at 15 degrees, the coffee starts to spoil. That's a bit of a problem. Now, as a bit of an extension to this one, because I've got to ask, I don't know if you really like coffee, but I would like to know if you know what the ideal temperature for brewing coffee is. What temperature should your water be at when you make coffee to make it smell so nice?
Isn't it 37 degrees?
Okay, I like hot coffee. I'm just saying, that's bath water. No, it's not 37 degrees. He's never making me coffee, in case anyone wanted to know. No, but thank you. No.
My director says 97.
That's impressive, actually. She's close. 1 degree out. I'm impressed, actually. Wow. She drinks a lot of coffee. In fact, the ideal temperature in your brewers, like your filter machines and stuff, should be between about 90 degrees and 96. So well done. If you're going to make coffee with boiling water in a bodum, those plungers, you actually have to boil the water and then wait, and then pour the water in. You don't want to boil. You don't want to use overly hot water, because if it's too hot, it actually almost burns the coffee beans, and then it's got no taste. If it's too cold, it doesn't extract the coffee. It doesn't actually allow the aromas and the flavors and stuff to come out. Bet you didn't know that.
Very interesting.
Hopefully, some of my learners are watching and they know what to bring to school tomorrow. I do not drink coffee in my classroom. I'm a very good girl. Anyway, moving on. And in case anyone wondered, I have a plunger, I have a coffee machine, I have one of those capsule machines.
What do you drink in your class if you don't drink coffee?
We're not allowed to drink in front of our students.
Oh, okay.
They're not allowed to drink in class, so I'm not allowed to drink in class.
All right.
We can go 30 minutes without having something to drink. Barely. Okay. Do you think we can go on to the next question, or are there questions you think we need to do?
We can go
Should
over
we
those
look
ones.
at it? Okay. So, here I've took all my questions from 2012. It was a good year. Okay. So, here we go. A group of learners use the reaction between zinc and sulfuric acid to investigate one of the factors that affect reaction rate. The equation below represents, it looks similar to the iron, but now we're using zinc. They add, this is why I chose this one. Ooh, that's the eraser. 6.5 grams of zinc to excess, very important, dilute sulfuric acid, and measure the mass of zinc used per unit time. So here they're giving us how we're measuring it. The learners then repeat the experiment using excess concentrated sulfuric acid. So what did they change? The concentration. Okay? How do I know that? Because I went from dilute to concentrated, still in excess. First question, define the term reaction rate. Well, the reaction rate is the rate at which the reaction takes place, the rate at which reactants are used up, same thing. But note it doesn't say for this reaction, it just says define reaction rate. Okay? And in the official memo, it said the change in concentration of reactants or products per unit time. Okay, so we're okay with that. Then, the next one says, give a reason why the acid must be in excess. This is an important question, particularly when it comes to drawing graphs. This is a reaction that must go to completion. And by changing the concentration of the acid, we could change where that completion point happens. In other words, how much product we make. By making the acid in excess and keeping the amount of zinc constant, the zinc becomes the limiting reactant. Okay? So we keep the acid in excess so that it doesn't affect the final product, the final amount of product produced. Okay? You could also say, why must the acid be in excess? So that the zinc is the limiting reactant. Okay? Also, so that only the concentration, there's many reasons here, and the concentration is the only thing that's being changed. Okay? Write down our hypothesis. Well, it's exactly the same as the last one we did. The rate of the reaction will increase when the concentration of the sulfuric acid increased. So we didn't do a hypothesis last time, we did an investigative question. So the rate of the reaction will increase if the concentration of the reactants increase. You could even write it like that. Okay, so we've got the relationship. Give a reason why the learners must use the same amount of zinc granules. I've just told you that because the zinc is the limiting reactant. Okay? Zinc is the limiting reactant. We want to make sure we get the same amount of product every single time. Okay? The results for the reaction using the dilute sulfuric acid are represented below. You are going to get a rate graph somewhere. Okay? Now they say, using the graph, calculate the mass of the zinc used from 0 seconds to 60 seconds. So they nicely drew these lines on us. So they tell us that the number of moles of zinc used, we started at 1. Now watch here, we started at 0.1. After 60 seconds, we have 0.08 left. We want to know the mass of the zinc used. This is stoichiometry. First thing we have to work out is how many moles of zinc were used. So the number of moles that we're going to be looking at is going to be 0.1 minus 0.08. I had 0.1, and I have 0.08, which means because we use our calculators, we've used 0.02 moles. That wasn't the question. The question is, what is the mass? Back to basic stoichiometry. Number of moles is mass divided by molar mass. We know that we've got 0.02. Little m is what we are looking for because that's the mass of the zinc. Capital M is the molar mass, and you would look it up on your periodic table. I don't know zinc's molar mass off my head, which is very sad, and that's 65 grams per mole. To get that on its own, you're going to go 65 times 0.02, and we're going to get 1.3 grams. It's tiny, small amount. Okay? We're not going to use a lot. We don't need to. Now they say calculate the average rate. Now this is new. In grams per second during the first 60 seconds. So we're looking for average rate. So let's say we're looking rate. Okay. We said that rate is changing concentration. In this case, we're using the changing mass. So we're going to do the change in mass of the zinc over changing time. Okay. And we used 1.3 grams. Okay. And we did that in 60 seconds. So we get a tiny number. 0.02 grams per second. I get the unit from the fact that they told me that it's in grams per second in the question, and I worked out grams, and I've got grams divided by time. Okay? Not actually anything too difficult. Now they say, on this, copy the above graph on your answer, in your answer book. On the same set of axes, draw a dotted line to show the curve that will be obtained when the concentrated sulfuric acid is used. Label the curve P. No numerical value is required. Please, before you draw this part, do the first instruction. Copy the graph. Okay? So in your answer book, you must have this graph. Copy the graph. Okay? Make sure you've copied what they have. You didn't need to put in the numerical value, so that's fine. Then they say using a dotted line. Okay, I'm pretty sure they said use a dotted line. Yeah, use a dotted line to show the curve obtained when the concentrated acid is used. Label the curve P. So concentrated acid means we increasing the rate. Increasing the rate means the curve must be steeper. So you still need to start here, and it's, okay, this doesn't even vaguely look like a dotted line. So let's try get this to look like a dotted line. Overemphasize, and then it'll get to the bottom. Overemphasize it. No numerical values, and they said label it P. No numerical values. You can't put values on this graph. They're looking for this to be steeper. Okay, that's what they're looking for. We
Awesome.
good?
I've
run
questions
out of
for you.
questions. Okay.
I've got a lot of them.
I'm sure.
Efres Matawata says, is it always necessary to include the gas, liquid, solid, and aqua subscript when writing any reactions? And by the way, AB mentioned that I'm the president. Okay, president?
Okay, president of anything. Rather be safe than sorry when it comes to that. It's a hard one. It depends on the reactions, but especially in rates and equilibrium, absolutely put it in. Yeah,
All right.
put it in.
Okay, Bongi Jamara says, when do we say that the reaction is favoring the forward reaction?
Okay, that's equilibrium. We're going to deal with that next week. Okay, not for rates. Nothing, that's equilibrium.
Okay, here's a comment from the guy who always watches the show with his mom,
Aw.
Jimmy. Jimmy says today, isn't physics, physical science is my favorite subject and favorite teacher? Well, watching alone today, my mom is at work. I feel sorry for her, enjoying the show.
Oh, shame. I feel sorry for your mom at work, actually. Shame.
Next one. And unfortunately, we can't get through this one, but I'm
Yeah.
just going to mention it. Diseto says, could you please explain using the collision theory how temperature and concentration has an effect on the rate of reaction?
Sure. That's actually explained in the notes, I think.
All
I
right,
think I
so
did,
get
yeah.
the notes, Diseto. Thank you so much,
welcome.
Tracy. It's
Yeah.
been a lovely show.
It was fun.
Thank you guys for watching the show. It's been awesome. And a big thank you to our crew. I must say, we've got a smart director, Belinda, and of course, a sound technician, Mr. Wilson Tembu. Well done, guys. You're a great team. Guys, this show was probably brought to you by the Department of Basic Education, and you must get yourself this awesome workbook by emailing sales@mindset.co.za. We love you, and up until next time, peace.